Happy Saturday, scientists. Let's review. As you can tell by the tie, we're doing some chemistry today, and we're tackling, in fact, C1, the first topic from paper 1 in chemistry, so it's a little bit of a shorter video today. So let's begin. It may be a shorter topic, but it's a topic that underpins our understanding of a lot of the rest of chemistry, and it will link into topics in biology and physics as well. So it's really important that we understand all the different parts of this topic. We begin with the particle model, and you will have seen these drawings a good many times where you have solid, liquid, and gas, and you're asked to draw the particles in each one. We recognize that the particles in a solid are touching each other, they're in a regular repeating pattern, and I'm drawing them in the center of the box to show that they do not take the shape of their container. Your key points are that they touch, that they vibrate in place, and that they don't take the shape of their container. In a liquid, we are going to have those particles able to move past each other, and that means that you can pour the liquid. It is considered to be a fluid, and those particles will still be close together. They will in fact be random instead of regularly arranged, and they can flow and therefore will take the shape of their container. And it's the same in particles or gases. They are far apart. They also have random motion and, relatively speaking, rapid motion. It is also important that you understand that the density is going to decrease. The more dense is the solid and the less dense is the gas, and that's because there are fewer particles in the same space. The next thing that we need to be able to do, especially those of you on the higher tier, is we need to be able to do some calculations with typical values. The typical diameter of an atom is on the order of 10 to the minus 11 meters, and you need to remember that. An example could be, for example, helium, which is the smallest, which is 6.2 times 10 to the negative 11 meters. And you might be asked to calculate, for example, the ratio between the distance that's between those atoms, for example, when they're in a gas, and the diameter. The problem would give you some information, so it might say that the distance is on the order of 3.4 times 10 to the negative 9 meters, and we already know the typical diameter, so 6.2 times 10 to the negative 11 meters. And we need to check that we are using the same units on both of these, because if we don't, we're going to end up in trouble. And so here we would end up with around 0.5 times 10 to the 2 as the difference, or you could say that it's 55 times. There are also limits to the particle model, or things that it doesn't tell us. It's not able to tell us about the forces. It is not able to tell us about the actual size of the particles, and it is not able to tell us about the space between the particles. These are the limits. These are the things that this model cannot tell us. And it's important that you know those three limits. So now that you know the particle model, some calculations associated with it, as well as its limits, we can move on into the next section, and we can move on into chemical versus physical changes. A chemical change produces a new chemical. It's as simple as that. You will often hear this discussion of reversible and irreversible, and I think that that is really beside the point. Chemical changes are difficult to reverse in a lot of cases, but there are cases of reversible chemical reactions, and so getting bogged down in this idea that chemical changes are always irreversible is not going to help you. In the same token, physical changes, which do not produce a new product, or rather no new product produced, these can sometimes be quite difficult to reverse. For example, if you were to rip up a sheet of paper into tiny little bits, that is a physical change. The paper is still chemically paper, but piecing it back together again is quite difficult to do. There are 4 main steps to the atomic model that we study in this course, and there are 4 main scientists who came up with these steps. The first of these is the Dalton model. And his model was that atoms were indivisible. So he looked at certain chemical experiments and he found that he always ended up with the same proportions when he broke things down. And he decided that there were these indivisible spheres of matter, and those must be the atom that the Greeks had talked about. The next scientist to come along was Thomson, and what he discovered as he was doing some experiments was he discovered the electrons. He realized that there were actually some parts to Dalton's indivisible model that were not quite so indivisible. What we now kind of qualify is that this model is chemically indivisible, but if we use some physics, we can in fact split the atom. And so Thomson's model created this positive sphere, and he put in the center or around this positive space these negative electrons that he had discovered. But overall, the atom was neutrally charged. And this is often referred to as the plum pudding, or the chocolate chip model, the idea being that the chips or the bits of the pudding are embedded within the positive sphere. This next scientist to come along was Rutherford. And what Rutherford did is the gold foil experiment, or he worked with Geiger and Marsden on the gold foil experiment, I should say. And what they found with that experiment is that particles were deflected from the center of the atom, and so there must be a dense nucleus in the center of the atom, and then electrons whizzing around the outside of this atom at random orbits, so kind of like planets around the model. And at around the same time, Bohr came along and he realized that if you had negative electrons whizzing around outside of a positive nucleus, the two would be attracted together. And seeing as they hadn't been attracted together and the universe hadn't imploded, then there had to be something that was keeping them apart. And so what Bohr decided is that there had to be specific energies that were associated with those electrons, and these became known as the electron orbits. So electrons in the Bohr model had specific energies, and they cannot be in between these orbits. So they must be in each of the orbits and not in between them. There are more complexities to these models, and I encourage you to go and kind of take a look at their development and to ask questions in the comments if you have them. But this is sort of the rapid timeline of the models that you need to know. And so what we have now arrived at is the atomic structure. So we know that the atom is formed of a nucleus, and that the nucleus is formed of protons, which have a mass of 1 and a charge of +1, as well as neutrons, and these have a mass of 1 and a charge of 0. And then outside of the nucleus, in the energy level, we have the electrons, and those have a mass that is much smaller, that is 0.0005, and they have a charge of -1. We can see that most of the mass of the atom is in the nucleus, and that the electrons really don't represent anything in terms of the mass. The next important thing to understand is that the protons are the identity of the atom. So they are the atomic number that you find on the periodic table. But atoms, it is important to understand, do not exist just in balanced proton and neutron numbers. There are atoms that have different numbers of neutrons, and those are known as isotopes. The neutron is the only thing that can change in the atom without changing the identity of the atom. So you cannot change the number of protons. So we're going to do a few examples of isotope calculations here. For those of you that ever need a periodic table reference, I highly recommend ptable.com. It's an excellent resource. Let's first look at nitrogen. So the little number next to the atom indicates the mass of that isotope. So it is a mass of 15, and we're told that the atom is nitrogen. Looking at the periodic table, we can find that the atomic number for nitrogen is 7, and so therefore the number of protons must be 7. And so to calculate the number of neutrons, we're going to do 15 minus 7, which gives us 8. So there are 8 neutrons in this case. And because no charge is indicated, we know that this is a neutral atom. It's not an ion. Next, we're going to look at carbon-12. So the mass in this case is going to be 12. Carbon, if we take a look, is here at atomic number 6. Carbon will have 6 protons. And then to find the number of neutrons, we would do 12 minus 6, which gives us 6 neutrons. No charge was given. There is 0 charge there. I should probably add a column here where we can look at the number of electrons, as this may be helpful when calculating the charge. So here the number of electrons has to meet the number of protons because there's no charge given here. Next, we've got an atom with a mass of 7 and proton number of 3. We know that the number of neutrons would be 7 minus 3, and that will be 4. And then we need to find what atom this is. So if we go and we look at the number of protons, we're looking for atomic number 3, and that is lithium. The isotope here we're dealing with is lithium-7. There is no charge given to us, so that must mean that there are 3 electrons and no overall charge. Next, we're looking at an atom with 24 as its mass and 11 protons. So we can discover the number of neutrons by doing 24 minus 11, and that gives us 13 neutrons. And then we need to figure out which atom this is. So we go and find atomic number 11, and we find that that is sodium. And so we know we're dealing with a mass of 24, but we're also given a charge of +1. So we need to indicate that there's that +1 there, and we need to calculate the number of electrons. A charge of +1 is going to mean that there is 1 fewer electron than there are neutrons. So if we visualize it this way, there are our 11 protons, and then a typical neutral atom of sodium would also have 11 electrons, and each of these would balance out, and there would be no overall charge. But if we have a charge of +1, that must mean that this electron here is missing because we're left with 1 positive charge. Instead of having 11 electrons, we must have 10 in order to get that positive charge. If you're finding these calculations difficult, there are some in the worksheet for this topic, and I highly recommend that you go and take a look at that, as well as with the other sections of this topic. There are a great many things here that will link to future topics in chemistry, as well as to the other subjects. Good luck on your studies, and we'll see you next week.